Alright guys, welcome to Math 0314, 7.4 Graphs of Quadratic Functions. So in this section we're going to graph what are called quadratic functions, but also called parabolas. And when we graph these parabolas, the goal is to see what sort of relationship that we can derive just by looking at the equation. Now, keep in mind, no matter what the graph is, if you ever don't know what the image is going to look like, you can just substitute values in. So what I'm saying is you can always make a chart, an XY chart, and you can just plug in values. So you can say, hey, if x is -2, plug -2 in here. What do you get? You get 4. Okay, so I have a point. Then you can plug in another one. Let's plug in -1. I'll get -1 squared, which is 1. I'll plug 0. 0 squared is 0. I'll plug 1. 1 will give me 1. I'll plug 2. It'll give me 4. So this gives you a list of points. So what I did in this section is I graphed this off of Desmos. And the reason why I used Desmos is what I just described is done in Desmos. So we have points, and you can see these points plotted all the way throughout the picture here, or the graph, right? And then you get a nice little image of what it looks like. The parabola looks something like this. And as you can see, as I trace over, the real reason why I did that was because Desmos gives me a much more accurate picture, so you can really see what this image looks like. So what we know about parabolas, what the graph of the quadratic function, of a quadratic function I should say, is that it's a U-shaped graph. And it typically, we can say it originates, or the highest or lowest point, in this case this would be a minimum value. The minimum value is what we call the vertex. The one I've graphed just now, y equals x squared, is called a parent function. And we've seen certain functions throughout this course, and so the idea is it's called the parent function because as you shift, as you add numbers to the function, it is similar, but it changes in some shape. So it might move to the left, it might move to the right, it may shift up, it may shift down, the graph might get smashed, or it might be expanded out. There's a lot of different things that can occur, and but it always has this U-shape identity. So this is why it's called the parent function. Okay, so in a nutshell, this is what's going on. One value that we will discuss later on in more depth is also something called this line that goes straight down. Now this line going straight down is a vertical line, and vertical lines we call our x graphs, and this is x equals 0. X equals 0 is something that I'm going to abbreviate AOS, but stands for Axis of Symmetry. And if you think about what the word symmetry means, it makes perfect sense. Symmetry means it's the line that when you draw it going down, it divides the function in equal halves. So what that means is, notice that whether I jump to the left or to the right, it's always a jump of 1. And there's a lot more values and interesting aspects to the parabola. For our sake, we're just interested in graphing it, figuring out what the vertex is, figuring out what the axis of symmetry is, whether we have a max or a min. In other words, is there a lowest point or a highest point? And then domain and range, which I haven't discussed yet, but should be pretty obvious. So domain is the x values, right? So the domain would be the x values. So the question in this graph here is, what are all the x values? Well, there's two ways of thinking about this. Visually, this parabola extends out to the left and the right forever and ever. So we can say the domain is -infinity to infinity, or all real numbers. Or if you just think about, are there any restrictions? Is there anything that you can't plug into x squared? Well, I can plug in negative numbers, I can plug in 0, I can plug in positive numbers, I can plug in fractions. There isn't really any restriction to what I can plug into x squared. It's always true. And if you're thinking to yourself, well, is there ever a restriction? Well, sure. We've seen section 5 began with problems like this, where we can't plug in 0, right? We've seen functions that, like the square root function, that you can't plug in negatives, right? So there are restrictions to the domain, It's just with the parabola, there never is. So that's, if you ever have a question that says, what is the domain of the parabola? What is the domain of the quadratic function? You can always put negative infinity to infinity, and you're always going to get it right, because that's always the case. And it should make sense as to why. Speaking of y, that's what the range is about. So the range is about the y values, and the way you want to approach this is ask yourself, where is the lowest point on the function? Well, we just talked about it. We said it was the min right here, right? So the lowest point for the y value, now make sure your mind is thinking about y values, is 0. And then because the function shoots up, right, it's going up here, and it keeps going up forever and ever, it's 0 to infinity. So because we're including 0, no, we're including it, we're going to put it in brackets, and then everything else becomes infinity. Okay? So we're going to touch base on these sort of properties in a little bit later on in the video. For now, what I'm concerned with is whatever I'm changing, how does that change the function? What happens to the picture? Is the picture going to be shifting left, right, up, down? And we're going to smash the picture, we're going to expand the picture. What's going on? So let's try to figure out what's going on. So let's look at the next one. We have y equals x squared plus 1. The question is, well, what does plus 1 do to the function? Well, we know that if we look at the last picture, right, we know that what we're getting here, right here with 4, 1, and 0, these are the y values, right? So we plug it in, we square a number, we square x, right? And then we add a number to it. So what is going to happen? Well, I'll give you a hint. It's either going to go shift, it's either going to go up, down, left, or right. Okay, so the question is what do you think is going on? Well, when we plug in x squared, we get a y value here, right? And then you add another number to it. So it would make sense that this would shift the function up, right? So it would make sense that it would shift it up. And if we look at this picture, that's exactly what happened. Remember, the last one, the min was 0, 0. Now it's 0, 1. And so what happens is this is now 5, 2, 1, 2, 5. If you compare to the previous one, let me erase this. They're just one more. So notice that the first one was 4, right? Then 1, then 0, then 1, and then 4. So everything went up. So if we look over here, everything's up. Plus 1, 5, 2, 1, 2, 5. And that's why you see all of these values shifting up 1. Makes sense. Moving on. We have y equals x squared minus 2. So it would follow that what would happen? And I'm hoping that you would say the graph would shift down 2, right? Because if plus 1 shifts it up 1, then minus 2 is going to shift it down 2. And we can see pictorially or visually that all of these values are shifting down. So I hope that makes sense. Let's move on to the next one. All right, so the next one is a little bit more complicated to understand, and that's what's going to happen when you add 1 to the inside. So notice that this is inside the parentheses. So what happens when you add 1 to x? So let's think about this for a second. So if we normally have, let me write this as the x values, and this is y equals x squared, and the other one's going to be x plus 1 squared, or y equals x plus 1 squared. Let's see what happens here. So if I plug in 1, or let's start with negative 2, negative 1, 0, 1, and 2. Let's see what happens here. So if I plug in, obviously here is going to get 4, 1, 0, 1, 4. Now if it's plus 1, let's see what happens. So if you have negative 1 plus 1, we now have negative 1 here. When we square it, we get 1. If we plug in negative 1, we're now going to have 0. 0 squared is 0. If we plug in 0, we now have 1. 1 squared is 1. If we have 1, we now have 2. 2 squared is 4. And if we have 2, now we have 3. 3 squared is 9. Right? So what you see, if you look at this, is that essentially these values correspond, but they're the one before. And this is why we argue that when we have, what does this relate to x, we actually have the value before. So in other words, another way to think of that is it's going to shift the function to the left one, because essentially it's the same thing as the value here, but it's one more to the other side. So it has to be the reverse situation, so it has to be shifted over one, so it's to the left one. So notice all these values are shifting to the left one. The big insight to grasp from this is that it's the opposite of what you think it is. So x plus 1 doesn't actually shift it to the right one, it shifts it to the left. Okay, and that's a very, very, very important point. It's always to the opposite side. Okay, so if this is minus 2, we think it's to the right 2. We're shifting to the right 2. And from the picture, you can see that that's exactly what's going on. I think the most telling point is always, and I've written over it, but the most telling point is always the vertex that we can now see has shifted over, which was normally at 0, 0, has shifted over 2. Okay? Now, what about if we have a 2 in front? Well, let's think about this again. X squared gives me the y value, and then the y value is being multiplied by 2. So this is doubling the y value, which means, another way of saying this is a vertical stretch. So you can see that what happens is as we go out, right, the function grows by a factor, the y value grows by a factor 2. What this does is when compared to the original, it actually makes the function more narrow. So actually, let's look at that. So this is a little bit more convoluted of the picture, but if we pay attention to these lines here, let me choose a color that we don't have here. Let's go with green. Okay, so in purple we have the parent. So in purple, the middle line, the middle parabola is the parent function, right? In black, I have 2x squared. So notice what happens. It's inside the purple, right? And so if it's inside the purple, that means it's got to be more narrow. And then it's the next one that we're going to look at. When you have 1/2 is the same thing as 0.5, but when we have 1/2 x squared, it's going to be on the outside. It's going to take longer for it to grow out because it's growing half as fast. So again, this is y equals 1/2 x squared, and what we can see is 1 normally goes to, right, or well, let's look at 1. 1 over here normally goes to 1. If it was just y equals x squared, it would normally go to 1. But now it's growing half as fast. So what that means is it takes longer for it to go up. So hence it's going to be a wider graph. So this is something else to realize, is that the bigger the number is in front of the function, what I really should be saying is the coefficient in front of the function, the larger the value is, the more narrow the graph is going to be. This is actually not even just true of quadratic, it's actually true of most functions. It tends to, I like to say, it hugs the y-axis more, the bigger the number is. And conversely, the smaller the number is, when I'm talking about this, I'm talking about absolute value. I'm not thinking about negative, which we haven't even talked about yet. But if the number gets smaller than 1, like in this situation, the graph is going to grow wider. So the common way of describing this is to think of a rubber band, and if you smash a rubber band, it gets wider, and if you stretch a rubber band, it gets longer. Again, kind of trying to show you an illustration of what I'm saying about these rubber bands is, if you have something like y equals 1/2 x squared, think of it as you're smashing the rubber band, and so it's shooting out to the sides, which means that your graph is going to be wider, is going to be a wider graph. Whereas if you have something like y equals 2x squared, right? Now you're shooting it up, which means that you're making the rubber band thinner, so it's going in, and so it becomes a thinner rubber band. So it's a nice little analogy to help you get your mind straight about what occurs in what situation. But let's keep looking at the next one. So the next situation is a negative x squared. So again, let's think about this for a second. So we know x squared, the result of x squared, whatever I get when I plug in a number in for x and I get x, the result for x squared, we're now going to just multiply that number by a negative. So what would that do to the y value? Well, hopefully it makes sense that normally this function was shooting up like this, but if we multiply by a negative, the function is now going to have to shoot down. And what I always like to say is, if you have a positive graph like y equals x squared, it means that you're positive, and if you're positive, then you're smiling. But if you have a negative graph like y equals negative x squared, like what we have here, then you're negative, and if you're negative, then you're frowning. So again, we can see here, it's the same, or the y values are the same exact y values as the parent, only now they're negative. Okay, so then what happens when we say negative 3x squared? So take a second now and think about it. You probably already know what the answer is. And I hope what you're saying is that what you've come to realize is that negative 3 means that it's negative, which means it's going to be going down. And then times 3, think of the rubber band, you're stretching it. You're stretching it by a factor of 3. So it should be going down and thinner than regular. Oops. So we'll see it's going down. And you can kind of see how it's a little thinner, right? It should be thinner because it's growing 3 times as fast. This versus this one, right? You can see where the points are. Here it's only going down a little bit. Here it's going down tremendous at 1. Okay? And similarly with negative 1/3, again, negative means it's going down. 1/3 should mean it's a wider graph. So if we look at it, we can tell that this is actually a wider graph. Okay? Now, in the next set of questions, it's going to ask us, it's going to combine everything all at once, and it's going to ask us to name the vertex, the axis of symmetry, the max and the min, domain, and the range. And the truth is, you don't actually have to look at the picture to know what this looks like. I do want to stress that if you completely forget what's going on and how to do this, you can just keep plugging in numbers, and you can kind of figure out what the answer is going to be. But let's try to think about what is going on without drawing the picture, and then we'll look at the picture to confirm our ideas. Okay? So when you're thinking about this, you should still follow Pemdas. So Pemdas, remember, is I like to call it math grammar. It essentially just gives you the order to how you should approach problems. So Pemdas says you need to do parentheses first, so we should be playing with the inside first. So what does x minus 3 mean? Well, remember, this was where we said we're shifting it, and it's counterintuitive, so minus 3 actually means you shift to the right 3. So this, whatever's going on, it should be shifting to the right 3. Pemdas then says, after we play with parentheses, we go to exponents, it's squared, so we know that because it's a quadratic, and then we multiply, so we have this times 2. And we just finished talking about this, the number on the outside stretches it by a factor of 2. So this is shifting to the right 2, this is stretching it vertically, technically vertically. You can actually have values inside here, which is beyond the scope of this class, but that would have a horizontal, that would be affecting it horizontally. This is a stretching vertically, right, by 2, by a factor of 2. And I said right 2, but it's actually 3, right, because the number is 3 right here. And then what is the plus 4? Remember, notice it's on the outside, so this is going to shift up 4, okay? So, again, just to rehash, 2 represents the vertical shift. 3, it's negative 3, which means it's the opposite effect. So we're going to the right 3. If it's related to x, it's always the opposite. And on the outside, we have a 4, which means we should be shifting up 4. So what would that do to the vertex? Well, remember, the vertex is normally at 0, 0. So shifting to the right 3 means now it's at 3, and shifting up 4 means it's at 4. So this point here is, we just follow those values, it's just 3, 4. Well, what about the axis of symmetry? Remember, when we looked at the original one, let's go back to the original. That was, oh, here we go. We got all this stuff here. Let me actually clear all of this out. We got a lot going on here. Okay, so what's going on here? Well, what's going on here is that the line shooting straight down here is the axis of symmetry. And this is at what? Well, we said this is x equals 0. Remember, when it's a vertical line, it's x. So it's a little counterintuitive, so it would be x equals 0. But in our example, what's going on? Well, we have x minus 3. So it would make sense that it shifts to the right 3, and so this is x equals 3. As a little shortcut, you can actually set it equal to 0 and solve, and you'll get x equals 3 if you want to. Now the next question is it a max or a min? Well, the answer to this question is very simple. Just ask yourself, are you smiling or frowning? Well, if it's positive, it means we're smiling. And if you smile, then what you have is a lowest possible value, which would be the min. We also said, when we were talking about this, we said the domain is always going to be negative infinity to infinity. You can never get it wrong. It's always negative infinity to infinity. And then the range remember we said for the regular, for the parent function, it's going to be at 4, I'm sorry, at 0, because the parent function, let's go back to the parent function here. Because the parent function starts at 0, right? So the range would be from 0, and then you go up, right? Well, what did we do with our example? I misspoke because I was answering for this problem, but we know that we shifted it up 4, right? So the range now, instead of being from 0 to infinity, the range now is going to be 4 to infinity. And again, you can graph it and look at the picture, and you can see exactly that, right? So the first question was, where's the vertex? 3, 4. Well, you can see clearly it's at 3, 4, right? It says, what's the axis of symmetry? Well, we don't have it drawn here, but you can clearly see that if I drop a line going straight down here, it would have to cut, in order to make it symmetrical, axis of symmetry, in order to make it so that whatever I go left, I go right the same amount, it would have to be going down, right down the middle here at 3, at x equals 3. Right? It's the only way it's gonna make any sense. So that makes sense. It's gonna be a min, right? Because it's right here. The domain is negative infinity, and the range, we can see it's starting at 4, and then it's going up. So that makes a lot of sense. Okay, so you don't have to actually graph the actual function. You can actually look at this. And so what I'm really trying to allude to is, if I have a more general format, what we're saying is that the vertex is HK. This is actually called vertex form because the vertex is HK. It was written in this format, right? And the axis of symmetry is always going to be x equals h, right? Should make sense. We also know that if a is positive, if a is greater than 0, then we know that the function is going to be opening up, and if a is less than 0 or negative, it's opening down, right? The domain, we say the domain is always negative infinity to infinity, and then the range is going to be what? Well, we know the range is based off of k, right? And so this is a little tricky, but if we have to make some stipulations here. If a is greater than 0, then it's going to be k from k to infinity, right? Because it's opening up, and if it's opening up, k represents the minimum value, so it would be from k upward. But if it's negative, now we're going down, so what do you think is going to happen? Well, k actually represents the max value, and this would be negative infinity. So in a nutshell, this is all you really have to know in order to answer these questions, right? So let's look at the next one here and take a second, pause, think about it, and think about what you think the answer is to this question for the vertex, the axis of symmetry, whether it's a max or min, the domain, and what's the range. So assuming you've given this a shot, let's talk about it. Well, we said HK is the vertex, right, from the previous, right? We said HK, where this is H and this is K. Notice, I want you to notice that it's minus h, so what happens here is we're going to write the opposite of whatever this value is. So here it's plus 2, so we would be writing negative 2. Now the y value is still going to be the same, so this is going to be negative 7/4. There's your vertex. Well, what about the axis of symmetry? Well, if we look back here, we said the axis of symmetry is x equals h. I said you can even just say x minus h equal to 0. Just take what's inside here, set it equal to 0, and solve. You'll get x equals h. So here, if we take x plus 2 set equal to 0, we get x equals negative 2. There's my axis of symmetry. Is it a max or a min? Well, let's think about what this graph is. So we know that when it's negative, it means we're sad, so we're frowning, which means that this has to now be a max value. So the vertex is going to be a max. We know the domain is always negative infinity to infinity because it's a parabola, right? It's shooting out to the left and the right forever and ever. And the range, because it is negative, because our a value is negative, right? We're looking at this situation here. So what that means is that it's going to go from negative infinity. This value of negative 7/4 is actually going to be my ceiling, my cap. Now let's see if we're right. Let's look at the picture. And of course we're right, right? It makes perfect sense, right? That this would be a max, right? We can see that it's shooting out. negative infinity to positive infinity, we can see that it's going down from negative 1.75. Remember, negative 1.75 is the same thing as 7/4. Think about 7/4 is $1.75, right? We can also see that the line going down here that cuts the parabola in equal halves would have to, of course, be the x value, which is -2. So it makes perfect sense, and that's it. So in a nutshell, this is all that's going on with parabolas. I want to stress that if you're struggling, if you ever forget the rules, you of course can just plug in points and start drawing the graphs. And a lot of times, especially if the question is multiple choice, you don't even have to know much, and you can just substitute in numbers and figure out what's going on. The only other thing I'll stress again, and I've said this a couple times, but I'll say it one last time, is that you want to realize that if it is positive, the parabola is smiling, and if it's negative, the parabola is frowning. And with that, hopefully this makes sense. And this is actually the last section, so if you've made it this far, congratulations, you have now completed Math 0314. That doesn't mean that I'm not going to keep making videos and helping you guys out, so if you need some help, you can always put a comment or you can email me and I'll get back to you as soon as possible. But congratulations, guys, and I still hope to see you in the next math video.